teachers and the students who have assembled here for this program from different AC schools. A round of applause is a small yet powerful way to show our gratitude and respect. So can we hear it once again? Thank you. The Gyan Samvardhan program is a unique initiative by AC schools and designed to empower students with knowledge, critical thinking skills, and a global perspective through inspiring and engaging talks by experts. We are truly honored to have Padma Shri Professor Shri Mustansir Barma, a Padma Shri awardee, to enlighten our students with his lecture today. We shall commence the program with the traditional lighting of the lamp. May I humbly request our esteemed guest speaker, Professor Barma, to light the auspicious lamp. We request the other dignitaries, Sri Ranjit Kumar, Chairman AES, Sri S.K. Lahiri, Secretary AES, Chairman LMC, Dr. G. Sugilal, Dr. Mrs. Nina Bopaya, Head Academic Unit, and Principal ACS 5, Ms. Ino Bansal, to be on the stage. Lighting of the lamp is symbolic of various things today, but here it symbolizes the illumination of the mind and the gaining of wisdom and understanding. Ready? 1, 2, 3, start. Thank you, sirs and Miss Dames. We would now like to extend a green welcome to our guest speaker, Padma Shri Professor Mustansir Barma. I request Rita ma'am to present the green welcome. To our esteemed speaker, sir, may this plant grow as a symbol of the flourishing partnership between our communities. May it remind us of the continuous prosperity and success of our endeavors together. Thank you. May I now request To begin our, to begin our event on a beautiful note, we will now be treated to a traditional welcome song that captures the essence of our heritage and spirit. Guided by Ms. Rageshwari, here is the ACS 5 choir extending a melodious welcome, a symbol of our gratitude and warmth to all present here. Thank you, dear children, for resonating the hall with your sweet voice. May I now request our dynamic and poised Principal and Head Academic Unit, Dr. Mrs. Neena Bopeya, to present the welcome address.
Honorable Dr. Mustansir Barma, Professor Emeritus, TIFR Hyderabad, respected Sri Ranajit Kumar, Chairman AES, respected Sri S.K. Lahiri Sir, Secretary AES, respected Dr. Sugilal, Chairman LMC, AECS and JC Mumbai, invited guests, principals, vice principals, teachers and dear students. A warm good morning to all of you. The Gyan Samvardhan program is an AEES initiative aimed at sharing knowledge, particularly in educational and academic areas. In this program, eminent personalities from various fields interact with students to exchange ideas, innovations, and research findings to enrich the students and to bridge the gap between classroom knowledge and outer world applications. It is my distinct pleasure to welcome all of you today to the talk on random walks in science and everyday life. We are honored to have with us Dr. Mustansir Barma, a distinguished expert in the field who is here to share his insights on this fascinating topic. Dr. Mustansir Barma is Professor Emeritus with the Tata Institute of Fundamental Research at the TIFR Center of Interdisciplinary Sciences, Hyderabad, and former Director at TIFR. After PhD from the State University of New York, Stony Brook in 1974, he did postdoctoral work at Michigan State University and joined TIFR in 1976. He has worked in the areas of non-equilibrium statistical mechanics, phase transitions, and disordered systems. Between 2002 and 2005, he served as chair of the International Union of Pure and Applied Physics, which is the only international physics organization that is run by physics community itself. Its members are identified physics communities in countries or regions around the world. He is currently a vice president of IUPAP. Dr. Barma has been conferred several awards and recognitions. Some of them are the Young Scientist Award of the Indian National Science Academy in 1980. He was the associate of the Indian Academy of Sciences from 1983 to 1986. He was awarded the Shanti Swarup Bhatnagar Prize for Physical Sciences by CSIR in 1995. He was the honorary faculty member at Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore from 1998 to 2001. He received the DAE Raja Ramana Prize for Lecture in Physics in 2004. He was conferred the S.N. Bose Birth Centenary Award of the Indian Science Congress in 2007. The same year, he received the J.C. Bose Fellowship of the Department of Science and Technology. The R.S. Goel Prize for Physics was awarded to him in 2010. Ladies and gentlemen, to crown it all, Dr. Barma was conferred the fourth highest civilian award of the Republic of India, the prestigious Padma Shri Award in 2013. Can I hear a thunderous round of applause for Dr. Barma? Today, Dr. Barma will guide us through this intriguing world, revealing how randomness and order coexist in ways that shape our reality. Without further ado, please put your hands together once again in extending a warm welcome to Dr. Barma. It was the ardent desire of Sri Ranajit Kumar, the Honorable Chairman AES, that Professor Barma should share his erudition with the students of our institution. Thank you, sir, for this noble thought and welcome to this program. I welcome Sri S.K. Lahiri, sir, Secretary AES, under whose able guidance and leadership AEES is marching forward. I extend a warm welcome to Dr. Sugilal, the Chairman LMC of AECS and JC Mumbai, principals, vice principals, staff, and students of ACES Schools Mumbai, and others who have joined us online. I welcome all of you once again. Thank you.
Thank you, ma'am. So we are very privileged to have Professor Barma with us here, a person of extraordinary vision, expertise, and impact. Without much ado, now let's welcome our esteemed guest speaker who shines with the brilliance of a gem, bringing clarity and insight that illuminate even the most complex topics. With immense gratitude and anticipation, may I invite humbly author, scientist, Padma Shri Professor Mustansir Barma to share his invaluable insights with us today. Please join me in extending a warm welcome to Sir as we look forward to his address on the topic. Thank you.
Okay, it will do.
Let us start it. Yeah.
Sorry?
Let us start it.
Yeah, sure. Okay, it's a really great pleasure and privilege to be here today. I thank especially Sri Ranjit Kumar and Dr. Nina Bupaya for all the arrangements and, of course, the invitation to come here. But the reason I'm really glad to be here, of course, thanks to you all, but to see all of you. Children, this talk that I'm going to give, I want all of you to try to get something out of it. Okay? And it's going to be an informal talk. I'm going to talk to you all. Right? And I'd like you to get something out of it. And if there's anything you don't understand, feel free to stop me in the middle. Ask whatever you want, and I'll try to answer. Okay? I know it's hard with a few, you'll feel a little constrained, but don't hesitate. Right. Okay, so let me get going. So I'm going to talk about something that's, a very strange subject. It's called random walks. Now, what is a random walk? You all know what a walk is, right? I'm walking. You go for walks every day. Good. But a random walk is different because you don't know how the walk will go. I'm walking here, but I may suddenly change my mind and back. Or might go here. I might go there. I also don't know what I'll do next. It's as if I'm tossing a coin. Okay, go here, go there. So it's random. So you get the idea? Random. Random means you're not sure what will happen. May go there, may go there. You never know. So let's see. Why would one even want to study random walks? But we'll see, I hope, as we go on, that there are many, many applications. Many in science and also in our everyday life, where for some reason, in some sense, we are always doing random walks. Okay, so let me try to convey this. All right. Yeah, can we go to the next slide? Yeah. Is there a clicker? Okay, okay, thank you. Thanks. So here it is. When you toss a coin, right, it comes up either heads or tails. When you toss it, do you know what will happen? You're not sure. It could be heads, could be tails. 50% chance this way or that way. That's an example of something that is random. You cannot predict what will happen. You know it will be either heads or tails, but which one you're not sure. Okay. Where does this happen? For instance, this path that I've shown here, I mean, you could think of me walking and tracing out my steps, okay? And this could be the path that is taken. Okay, you start somewhere here, let's say, move this way, that way, and land up somewhere else. But actually, this is a scientific measurement that was made many years ago. It's not a random walk taken by a person. It's a measurement of a single particle put in a liquid. Okay, so it's hit by molecules. Do students, you all know what a molecule is? Oh, wonderful. Okay, great. We'll be talking about molecules. So these molecules come and hit this particle, but they hit it randomly. It goes here, then it goes there, then it goes there. You know, doesn't fall off. You know, it keeps going, moving left and right. And this was actually the measurement done of a single particle as it's hit by molecules. And as you see, it follows what we might call a random walk. The last example that I'll come to, very strange, cars on a road. You've all driven in the city, right? I mean, I know you have not driven, but you've been in cars in the city. Which city is this? Mumbai. How do you know? Taxis, yellow and black, Kali Pili, right? This is our trademark. Okay. So now, so think about it. You know, so you have a road, you have cars. Everybody should be driving very nicely, straight and smooth. But do they drive like that? No. People go left, they go right, they go straight, they suddenly put on brakes. You can't tell when they'll do it. It's all random. And because of that, there are very strange things that happen in traffic, like traffic jams, you know. So we'll talk about that as well. So this was just an introduction to tell you what we will be talking about. Let's go. Let's move to the next slide. Yes. Right. Let's go ahead. Okay. So in this graph, what I've tried to do is to show how a particular particle moves in space and time. So it starts here, let's say, at some point in space. After one time step, this particle actually moved left. Next time step, it moved right, and then left, and then right, and so on. Okay? So what you are seeing is in space and time, what the particle did. If you have this in front of you, you can tell exactly after 5 time steps, where was it? Is this clear to the students? Good. Okay, so this is an example of a random walk, but shown in space and time. Now, because it's random, we can't be sure where the guy will land, where the walker will land up after, let's say in this picture, there are 17 steps. After 17 steps, where will the walker be? We are not sure. Could be here, could be there. So we're not very sure, but the question is, after some number of steps, let me call it capital N steps, okay, 17, 18, whatever, how far is the walker likely to be? Okay. Will he be 17 steps away? Probably not. If I had taken 17 steps this way, I would have been 17, a distance of 17 away. But my steps are random. So it can't be 17. It must be something small. What is the likely answer? what we will show, we'll see, is the answer is square root of 70. Children, do you all know what square root is? Yes. What is it? You take the number and you multiply it by, get the answer, right? So square root is that number which when multiplied by itself will give you the number that you started with, right? So if I have some 200, say, let me take a number which is easy to take the square root of. If I have 100 steps, can somebody tell me what is the square root? Oh, that was quick. What about square root of 256? 16. Oh, good. And square root of 1024? Very good. So can you imagine a walker taking 1024 steps? At the end of it, where will the random walker be? Only a distance 32 units away. So what's the square root of a 1 million? 1000. Very good. So after a million steps, the walker might have wanted to be a million steps away, but won't be. Only just 1,000. Okay, so this is the nature of what is happening. Can we go to the next thing? Okay, so it turns out that this sort of movement, or this sort of chance events, are very important in many, many fields. You can imagine mathematicians will be very interested in this because they love to solve problems where you're not sure of the answer, but you somehow figure out what will happen. People in physics are very, very interested because we'll see that these sorts of motions actually happen all over the place in real systems. And in everyday life, as I said, there are important applications. I don't know whether we will have the time to reach the end, but I would like to talk a little bit about traffic, especially in our city or somewhere, and movement crowds. When people move in large numbers, they also do quite random things. So the effects of those are very, very interesting. So we'll come back to these effects in everyday life. Next, please. Okay, so here is path traced out by a random walk. It's just going left and right, in any direction, and landing up, starting with that first red dot to the last red dot. Okay. Where does this happen without actually having a person walking like this? So let's look. There's something that's called in science, in physics or science, Brownian motion. Now, many of you may not have heard about Brownian motion. Don't worry. It's just the following thing that if you put particles which are, let's say, 1 micron big. Now, how big is 1 micron? Anybody know? Good, I'm hearing some right answers. You're familiar with centimeter, millimeter. So divide the millimeter into 1,000 parts, and that will give you 1 micron. So these are small particles immersed in a liquid, and as I showed earlier, they perform random walks. Second situation. Imagine that you have a solid. See that here? Here. Solid in which there are many atoms. They're all arranged in a nice square arrangement. But nothing is perfect. So quite often in a solid, you have one missing atom. Can you see that one? There's one space which is not full. Now what happens if you have a temperature, is that there are 4 atoms around that space, and any one of them can hop into that space. Could be this, could be that. Now let's say this second, the one on the right, moved into that space. So you could say that happened, but the better way to think about it is that the space itself has moved. Do you understand what I'm saying? It's an atom which is moving. But once it moves, where it moved from is the new place which is empty. So the empty space does a random walk in the lattice. And the way it does the walk, etc., is very important to figure out um, very important to figure out the properties of this material. Okay. Uh, let me skip the third example. It's a polymer, and we'll come back to that in some way later. Let's go ahead. Now, so I wanted to interrupt the talk a little bit. You know, we're talking about random walks, etc. But let me tell you a little bit about what should we be doing in science. Now, you're all students. You'll all appear for examinations and tests and whatnot. And what do? You get a question paper, and what do? You put in your answers. So often you think, you know, the answer is very important. It is. But in science, what's more important than the answer is really the question. You know, so ask the right question and you'll get an answer. So you have to come up with the idea or the capacity to learn to ask the right question. And in science, everything happens because people ask the right question. So let me say something. What is it that we keep trying to do in physics? We want to understand what is really going on in terms of some simple laws. Have you heard of Newton's first law? Anybody? What about Newton's third law? Tell me what the third law is. Okay, quite right. Well done. Okay, Newton's second law is a little longer to say something about. We won't ask what. But so these are laws. Laws means something so basic that it underlies everything. Okay. But to find what the law is, you have to ask the right question. You know, you can't just say, okay, Newton didn't sit there and say, okay, third law, this is what. No. He asks the question, what is going on and how does it fit in? So that's what I'm trying to emphasize. And what do we mean when we say we understand? You have something very complicated going on, like taxis on Mumbai roads. You know, is there something simple that you can say about the whole thing? If there is, then you can say you understand something. Okay, right. So here, look at this. See, there's a. Can you all read? I mean, from that distance? I hope so. Anyway, so these guys are so busy working out the answer. They filled the blackboard with equations. They found the answer, but they've forgotten the question. So that is no use. Cling on to the question. Answers could be right or wrong. It's okay. We'll come to the right one. But question is important. Okay, so remember this. Always ask the right question. And you know, the history of random walks started with a question. So can we go to the next one, please? Yeah. Next. Yeah. Thanks. So this is the question. The scientist in the early 1900s, 1900, so 100 and odd years earlier, his name was Carl Pearson. He was a statistician and he asked a question and sent it to a journal and asked, can your readers tell me the answer to the following question? And then he defines what we call the random walk. He says, a man starts from a point O, which is shown in red there, walks L yards, then turns and walks L more yards, etc., keeps doing that N times. And then he asked, you know, I want to know the probability, I'll come back to probability, that the man is R yards away from the starting point. Children, does this question make any sense to you? Yes, okay, good. So, yes. Oh, wonderful. Okay, so can you all see the pointer? Red, yeah. The person starts here, goes in some random fashion, takes many steps and stops. At that time, at that point, how far is he from where he started? We're not sure, but we want the probability that he'll be a certain distance far away. So, notice the date. Oops. 1905 July. All right? And he sends this question across. Okay. And here's the answer. So within 2 weeks, somebody has told him the answer. And in early August 1905, he says, I have to thank many people for telling me what the answer is. And the answer goes back to the work of a famous scientist at that time, Lord Rayleigh. And he says the lesson of Lord Raleigh's solution is that in open country, the most probable place to find, okay, excuse me, but a drunken man is somewhere near his starting point. So this is the first time that this idea of a drunken person was put in to have a clear picture of a random walk, because somebody who is not in his senses will move this way, that way without thinking and land up somewhere. And you can see a picture of somebody starting at this lamppost but going all around and landing up here. So this is the first time that this word random walk, the problem of the random walk was refined. But remember, it's the question. It's the question he asked. It took some time to find the answer. Answers will come, but the question was a good question. How can I find the probability that somebody is this far away after taking so many steps? So here is an example of a random walk. 1,000 steps. And you can see this tangle thing. Okay. What is the rough square root of 1,000? It's about 32, right? That you all told me a little bit. So whereas this, if you actually follow these steps, there will be 1,000 of them. This start to finish distance is much smaller. It's roughly 32. Okay, let me go ahead. So here it is. Here's the point, actually doing a random walk in front of you. You can see how it's building up. It's moving left and right and back and forth and so on. And you see that it's not doing something very simple. Sometimes it goes and keeps going around this place it was. Sometimes it darts away. So this is what it looks like in the end. It's as if you had a ball of string and you sort of made a big mess of it, and you have a little bit here, a little bit there. And then your mother tells you, please sit down and open it up. Okay, you can do it, but it takes time. But this is what this reminds you of, right? Okay, let me. So, have you all heard of Albert Einstein? Okay. What did he do? Anything? I mean, any subject, anything that he did? The theory of relativity is indeed what he is most famous for. And you know, when he did this was in the year 1905. But in the same year, he also wrote a paper on what is called Brownian motion. And he had an idea. And the idea was very simple. He said, look, you have a beaker of liquid and you have molecules and they're all moving around. And you know, the hotter the liquid, the faster the molecules will move. Okay, very good. And they move in some way and so on and so forth. But suppose you had a much bigger object, which is much heavier, like a colloidal particle in the liquid. Well, so you think that is quite different from a single molecule, because the colloidal particle itself is made of many molecules. But Einstein said, never mind. It's just like a big molecule. So this was his insight, that if you put a particle in a liquid, it behaves like a large and heavy, but not very different. So he actually suggested to anybody who wanted to do the experiment that please follow the motion of these things. It will be like a random walk, but by following the motion, you will be able to find Avogadro's number. Have you all heard, any of you, of Avogadro's number? Okay, tell me what the value is. Absolutely right. Okay. This is a very strange thing, telling all of you. If you ask anybody what Avogadro's number, they'll tell you. And they'll tell you to 3 decimal places. They won't say 6 times 10 to the 23. They'll tell you, this is what I heard from all of you also, they'll say 6.023 times 10 to the 23. It happens only for Avogadro's number. If you ask somebody what is the speed of light, no student will. Sorry, can you tell me? Okay, one person. Yes, can you tell me? Anybody? Put up your hand and I'll say. Speed of light? Yes? Right, this is what I meant. So the answer is 3 times 10 to the 8 meters per second. But nobody quotes it to 3 decimal places. So Avogadro they'll always do. Anyway, now the strange thing about Avogadro's numbers, Avogadro did not know what the number is. He knew there's a large number, but he did not know how big it is. So it could be found only by doing an experiment. And this is what Einstein suggested. Do the experiment and you'll find it. So then, who did the experiment is shown in the middle of the slide. His name is Perrin, okay, French scientist. And what he did is that he carried out exactly Einstein's instructions of repeatedly looking at how these particles move. From that, he was able to find, so he was able to find the effect of temperature on this motion, and through a set of arguments, which I will not go into, you can actually find the Avogadro number. Okay. All right. Let me move on. Okay. Yeah, maybe we wait for some time. Carry on? Yeah. Okay. Yes. Please come. Yes. I couldn't hear. Can you repeat? Why is what? I'll show you in 2 minutes. Yeah. I'll give you an. Yeah. You wanted to know why it is square root of n? Yeah. I'll tell you in about 5 minutes. If you can sit and just wait, I'll actually show you that it has to be square root of n. Okay. Wait a little more. Okay. Thanks. Okay. Now, this measurement by Perrin was very, come have a seat in the meantime, was very, very important because, until he did the experiment, there were many scientists who doubted that there are objects like molecules. To us, the fact or the existence of molecules is sort of very much part of what we learn and what we know the world is made of. But until he did this experiment, there were many, many people who doubted it. Okay, very well-known physicists. I won't go into the detail. This experiment was one of the first experiments which enabled anybody to find the value of the Avogadro number. And the last thing is that, if you look at these random paths here, they're not at all smooth. They're very, erratic. And mathematicians became very interested in them. Norbert Wiener is a famous name, and he was inspired by looking at these graphs to come up with a very nice notion in mathematics that's called the Wiener measure. Let's not bother about that. Okay, now random walks come in all sorts of situations. So here's another situation. I have a large number of spheres, okay? They're hitting each other, they're moving randomly. But if you watch this a little bit, you'll see that if you look at any one sphere, you see something white there. So look at the path that's followed by a single particle over there. This path is in 3 dimensions, but it is actually nothing but a random walk. Okay, so this walk happens not because the single particle wanted to walk around randomly, but because it's hit by other particles and it cannot move. But you see that the trajectory is indeed one which actually resembles a random walk. Now, this reminds you of something that you may or may not have come across in school. Did you know that, when you have a gas in a closed container, it's the molecules which hit the side of the gas which give rise to pressure. Did anybody know this? Oh, great. Good. So this goes under the name, not important, of kinetic theory. And usually if you ask any practicing scientist, who is the person who came up with these ideas first, they'll say Maxwell or Boltzmann. They're both wrong. The first, I'll tell you, is very interesting. The first person to come up with this notion of molecules producing pressure and their speed determining the temperature, this was done 15 years before Maxwell, and it was done where? Bombay. Now Mumbai. 1845, it was called Bombay. This fact is not known even to practicing scientists, but you all should know this. This is one of the great things about our city. So let me tell you a little bit about this story. It's a story about somebody who discovered something but was not given enough credit. Okay, so go back to 1850. Okay, some long back. Here is this person, Clausius, who worked on these problems and is very well known today. Here is Maxwell, very great physicist who also worked on it, very well known. But here is the third name. Very few people know about this. Name is Waterston. Okay, and he was the first to understand molecules produce pressure. The speed with which they move is determined by the temperature. So this was a great discovery, and let me just tell you about the history a little bit. Who was Waterston? So Waterston was employed by the East India Company. You all know about East India Company, right? And his job was to teach the naval cadets of the East India Company some mathematics. But he had a lot of spare time. In that spare time, you would think, maybe these molecules are doing this or that or something. And he wrote about this in a large manuscript. Okay, first of all, where did he do this work? He did this sitting in the library of Grant College. Grant College is probably Grant Medical College today, but this is what it looked like in the 1850s, long, long ago. Have you all heard of Grant Medical College? Okay, it's a famous college, trains doctors in the middle of the city. Okay. But then when he wrote this manuscript, he sent it for publication, but it was rejected. The journal thought this is nothing but nonsense. Who said there are molecules? I mean, the journal said this is an outlandish idea. Why do you think there are molecules? Well, so to his bad luck, it was actually rejected. But 50 years later, somebody found his um, work and republished it, and that is how we know about it today. But in fact, the work was done far before the names that we normally associate with this. But I thought I must tell you all this because we are from this city. Okay, let's go ahead. Okay, now I want to spend a little time on some very, very strange properties of randomness. The first one is square root of n. Where does this come from? Okay. So I'm telling you without proof right now, but I'll give you the proof in 2 minutes, that after time t, if you have this walk, the typical distance moved will be square root of t, proportional to the square root of t. It will not be proportional to t. Okay, so why is that? Let me try to illustrate. So, I'd asked for a blackboard here, but the blackboard would not be seen by you all at the back. So instead, I've just videoed myself writing this derivation. Is that okay? Okay, so here. Oh, there's no audio. Whoops. Can we put on the audio? Okay, I'll supply the audio, don't worry. Okay, let me go back. Okay, so let us call the place where the particle is at time t, let me call it x sub t. Okay. Now let me take one more step. So I have x of t plus 1. Okay. So that is equal to x of t plus some quantity y, but that y must be plus or minus 1 because here it must have started there. Is this clear to you all? Okay, let me halt if I can. I mean, how do I halt? Oops. No. I'm not sure how to halt, but okay. Okay, I'm sorry, we'll have to run through this. Is there a quicker way? Is there a better way? Audio is there. Okay, it doesn't matter. Audio will supply. So just keep going. Yeah. Anyway, come back to that equation. X of t plus 1, x sub t plus 1 was equal to xt plus y. And y is plus or minus 1. Is that's important to understand. Do you all understand this? Yeah. Because it must have been here or there before it came here to t plus 1. Okay, so let me catch up with that. The next step will be, we will take a square. And you'll have to remember what a plus b squared is. Does anybody know? Very good. So that's what you have to know. Keep going. Yeah. Okay. So let's square this equation. What will we get? X t plus 1 squared. Okay. So I wanted to remind you that y is plus or minus 1. Okay. All right. Just make sure I'm doing it right. Huh? Sometimes I make mistakes. Is this okay? So far, so good, right? Next step, we take an average over different random walks or different histories. Okay, so let's do that and see what we get. This means average. Okay, that happened. But y is plus or minus 1. So what is y squared? 1. So plus 1. And what about that last one? It's 0. Because the average value of y, what is the average of 1 and minus 1? 0. So that last term actually gives you 0. So x of t plus 1 squared is xt squared plus 1. Now from there you can easily find that xt squared average is equal to t. This implies try it out. At t equal to 0, x is 0. At t equal to 1, it's 1. At t equal to 2, it's actually 1 plus 1, 2. At t equal to 3, it's 2 plus 1, 3. Therefore, at any time xt squared is equal to t. So the square root of xt squared, which is the typical distance, is square root of t. Okay? Okay, so that's the answer to your question. Let me move on. You know, it's a simple derivation, but it needs some thinking. All right, I'll go ahead. So, top answer we've given, right? After time t, a typical displacement is indeed root t. Okay. But suppose I ask a different question. I'm starting here. I'm doing my random walk. Will I come back to where I started? Now, the answer is yes. With probability 1, you will come back if you are doing the walk in one direction, or if you're doing it in 2 dimensions. But for doing that random flight in 3 dimensions, the answer is no. So this is a very interesting result proved by Polya, which says that if you start from somewhere, you definitely come back. But it doesn't tell you when you will come back. Okay? So let us take this for granted. Let's say we are in 1 dimension, meaning that I'm not moving this way, I'm moving only this way, along this line. Then, but now let me ask you a question which really confounds you with the answer. How long will I take to come back? Or let me ask a simpler question. I'm here. Neither go here, you can go there, right? Now, my question is very simple. How long will I take to reach the site next to me? On average, you can't predict. So with 50%, go there in 1 step. But then I might have gone this way, and then it may take me a little longer. Okay, so children, how, rough guess, how long do you think it will take to reach the site next to? 10? Okay, and any other answer? 5. Okay, somebody else? No, you can, okay, I'll tell you how you can define it. Doing the average of to reach. Okay, just that. Okay, so I have a lot of answers, 2, 5. Anybody with an answer larger than 10? 30, okay. All right, so let me give you the answer. The answer is infinity. It takes infinitely long to come back. It's very strange, but it's true. Why does this happen? Because if you move left and you come back, you may not come back right there. So you have to average over every possibility. And when you do that, the average turns out to be infinitely large. Now, I want to keep this slide because the answer is so strange that many people did not believe it. How can it be? But you can show mathematically. I will not show now. I mean, that this is true. But it's very odd because just before this, I said, you are definitely coming back. You will come back. But it will take you infinitely long time to come back. Okay, so this is the very strange thing about this. Now, this has a very practical and important what should I say, important consequence in playing games. So this is known as something called the gambler's ruin. So okay, so I need one volunteer. Anybody? Tell me your name. No. So Anjur and I are supposed to be playing a game. And the game is very simple. I'll keep tossing a coin. Actually, I have a coin we could toss, but we won't do it. Let's imagine. If there's a heads, let's say, if there's a tails, Anjur gets 1 rupee. If there's a heads, I get 1 rupee. Okay, so the simple game. Now, we keep doing it for a long time. So if we make 1,000 tosses, of course, roughly 500 times I'll have to pay you, and roughly 500 times you'll have to pay me. But let me ask a slightly different question. We're not interested in the actual amount of money, but who is winning at that time? Just that. So let's follow this sequence. Okay. So let's say the sequence was tails, heads, etc. Now, every time you get a tails, we'll have one more volunteer doing a left step in the head, the person will do a right step. Okay. So it's obvious that any sequence like this will become a random walk. I mean, do you all see what I'm saying? Tails and heads, you can, in a different language, talk about a random walk. Okay. Now remember what I said, that come back or even move one step right takes very, very long. So here is an actual coin tossing where the coin was 10,000 times. Okay, and see what happens. You see all these dots. If they are above the axis, that means you're winning. If it's below the axis, I'm winning. Okay, so we start and you're winning, so I feel that I must get back to you. And for sometimes there's some change of please. But now look at this. A very long time, there's no change. He wins. Look at this stretch. It's 3,000 steps long. The 3,000 times he's tossing and it keeps the lead. So the lead in a game like this is going to be very long because time taken by a random walk to come back where it started is very long. So this feature is sometimes called the gambler's ruin. So when you go to gamble, I mean, please don't, but if you do, then, if you lose the first time, the best thing is to get out of the game. If you lose 1 rupee, I lost the rupee, I felt that I must get it back. 1 rupee, all should be able to. But it will take. So if I have, it's a little dead. Can you hear me? Is this on? It is on. Okay. All right. So long as it's on, it's fine. Okay. Thanks. Okay. Great. Yeah. So what I was saying is, yes, you will supply of capital. Okay. All right. So is it the mic or is it me? Yeah. All right. Okay. Let me go ahead. Let's this part and let me come to something else. Okay. Maybe at this point, we ask for questions if there are any. Any questions, please? Anybody? Front row. Okay. Children anywhere?
Hello, sir. I have a.
Where are you?
Uh,
Yeah.
Sir,
Yeah.
is there a possibility that the random walk is in a straight line? And if so, how big is it? How small or
I couldn't actually catch the question. Is there a possibility that what?
the random walk is in a straight line?
Good. Very good question. Yes. Now, so the question is there a possibility that the walker keeps going left? Is that what you mean by straight
Yes,
line?
yes, sir.
Yes. Yes, there is always a possibility because nobody can stop that. But if you take n steps, let's take a certain number. Okay, 100 steps. There's a certain probability that you will actually keep going straight. But find what the probability is. The answer is that it's 2 raised to the power minus 100. Okay, so in other words, 1 over 2 to the 100. Now, these children are excellent at estimating. So, can somebody tell me what is the value of 2 to the 100? Not that easy, but roughly. I couldn't hear. Good. So, here's the answer. It's 1024 raised to the power 10. But 1024 is 1,000. So it's 1,000 multiplied by itself 10 times. So it's a very large number. So the probability of this happening is 1 divided by this very large number. Okay. It's possible, but with probability, but it has a probability which becomes 0 as the number of steps becomes large. Okay. But
Thank you, sir.
very good question. And this is an important thing for you all to understand. This is probability. We don't exclude anything. Anything can happen. That can happen. This can happen. You can keep going. But you have to figure out what are the chances. And the chances are practically 0. Is this
Thank you, sir.
acceptable? Okay.
Yes, sir.
Thanks. Whereas, the probability of coming back to exactly where you are in n steps is very, very large. You can find out what it is. But I won't go into that. Yes, Ranjit Kumar. Yeah. Uh-huh. Right. So there are 2 ways of approaching it. So one is to give a proper mathematical definition of randomness, which I will not do. The other is a coin and toss. So take that as an experimental way to have randomness. By the way, the only physical process See, when you toss a coin, actually it is governed by Newton's laws and everything. The answer is deterministic. But the only natural process which is truly random is radioactivity. That is truly random. And you can set your measure by radioactivity. But I'm trying to use the notion of random in a colloquial way, which we think we understand. All right. But the actual definition is difficult because, yeah, okay, for various reasons. Okay, so with your permission, I'll carry on. Okay, and now what we're doing is we're looking at many random walkers. Okay, all right. So far we had one guy doing the random walk. Suppose we have a whole lot of them. Now the reason I'm doing that is slowly I'm going to head to traffic. Ask you to think about this question. Okay, right. Here we are. This walker starts here, this there, this there. And suppose this is in one dimension, but the walkers cannot overtake each other. Then whatever this walker does, it cannot cross the next one or the next one or the next one, right? If you look at the trajectories, namely if you look at where the walkers are after some time, they'll be all over the place, but only there will be one rule that this line has to be between these lines and this line has to be between those two, etc. Okay. You could have other things happening. It could be that two walkers come and bunch up and become one, and then they move, and then they follow the process like this. Or you could have electrons and positrons. Anybody heard of positron? Positron is an anti-electron. An electron and positron meet, they annihilate, they go away. Okay, so here we are. The last picture shows that. Here's a let's say an electron, and here's a positron, each doing a random walk for some reason, and wherever they meet, they annihilate. Okay, so I'm just trying to tell you, you can have various sorts of. There was a question from somewhere here. Somebody had a hand up. No? Not a question? Okay. You just had a stretching. Okay, good. All right, good. All right, let's go ahead. Okay, let me just, I beg your indulgence for two more slides and then it will become much, much simpler. So as we said, if we have these particles which are moving, they are allowed to move, but not, this particle cannot move here because there's another particle already. Well, then you get these pictures like this. Now, suppose ask, I am a random walker, all of these guys are, but more likely to move right than left. Okay, so let me do that. My right, your left. I'll take many more steps right and left. If I do that, after some time, actually I've moved right. Would you agree? Whole, I'll move rightward, you know. That is what happens, and then you get pictures like this. But why am I doing this? Because I'm going to argue in a minute that this, oops, what am I doing? Sorry. That this sort of random walk motion with many walkers is not so different from the movement of cars on a narrow road. Okay, this is where I'm heading. So let me now head that way. So this is a slight change of, you know, nature of the talk. I'm going to talk about everyday life now. Enough science for the moment. Let's turn to traffic and crowds. Okay, let's see what happens. All right, so here are two pictures. The left-hand one is just showing long exposure in the evening when cars are moving, and you can just see the tail lights, they're red, and they're all moving away. And this one is an exposure of people on a railway platform. There's a crowd, and it's moving in a particular way. Now, we are not going to say that a person in a crowd like this person, that nobody in a crowd is able to do a random walk because it's so crowded, right? I mean, you can't move left and right that easily. So it will have to be that we think about random walkers, but with some extra rules which incorporate what is going on in a real crowd or in real traffic. So let me tell you. So the common thing in both of these, it's a little unfamiliar way to think about it, is there's a current. What current? Electric current? No, it's a people current. It's a car current. The cars are moving. They actually have a current. I mean, you put a measurement and you'll see many cars going. You measure how many go by. That tells you what the current is. So the things that are giving you the current are not electrons, as they are in a copper wire, but objects like cars or people. The only thing we have to watch out for, see, electrons, once we know something about the electrons, we know all electrons will behave in the same way. But not true of people. Every person is different. Not only is every person different, it depends on the mood of the person. Some people, today I'm feeling great, so I'll drive fast. Today I'm not feeling that great, I'll drive slow. Something. Today I just want to put my brakes. Ridiculous. People are not like electrons, for better or for worse. So that's what I've said. The current carriers are very individualistic. They have their own temperament, their own moods. Let's see. Now, here's one. We want to model traffic. And we want to think of these random walk type models to do that. Can we do it? How do we do it? So, traffic has been studied for years by traffic engineers. But then suddenly the physicists got into the act and they said, we want to study traffic. So what did they do? They built this model which sounds very odd and strange and doesn't seem like it should work. So the first thing they did is they said, instead of a road, let's consider boxes which are a little bigger than each car. And the cars can move with different speeds from one box to the other. But of course, they cannot crash into another car. Okay, so you put these rules in. So the two people, Nagel and Schreckenberg, names don't matter so much, but they tried this model and it seemed to have some things in common with real traffic data, but they could not get it to really work until they put in this element that every driver is unpredictable. Usually predictable, but with a small probability, the driver will do something that you cannot predict. For instance, apply a brake. The moment they did that, the data fell in very well and reproduced the data for real traffic. Now, so you might think this is such a simple and primitive model. Will it actually work at all? Well, the answer is actually it worked very well to the extent that the German traffic highway authorities actually used this model to make predictions on how traffic will go, and it worked very well. And they were able to provide 1 hour forecasts for the best way to go from A to B. Now, a strange thing happened when they made these forecasts. This is before, before what's it called, Google Maps and all that. This is long back. These results were given on the radio. So now this is a question on psychology. Let me ask one of you. Suppose you want to go from A to B, or one city to the other, and there are two ways of going, way A and way B. And then you've done this calculation, you know the way B will take longer because there's more traffic. So which road would you take, A or B? Are you sure? Why B? No, you have to have another reason. Because everybody is listening to the radio. So if everybody is listening to the radio, everybody will therefore think of taking road A. But then road A will get crowded. So I should take road B. So road B is, but then you're not sure because, you're never sure. Should you take A or B? Okay, radio is saying take A, but others are listening, so they'll B is better. Anyway, so, well, they did a survey and they found there are three groups of people. Group one takes road A because the radio has said. And they're 30% each. Huh? Group B takes B. They think they're being a little clever. Road A, so let me take road B. Third group is a group of people like me who sort of undecided to the last. They just go there and they decide at the last minute. I'll take A or B without thinking. Okay, so this is an actual survey done of people, and this is how people behave. People are people. They are not predictable. This is also very important when you come to crowds. Okay, before I leave, I think one of the most important applications of traffic in science is when we're dealing with what are called molecular motors, which move along highways, uh, biological highways in our body. I won't get into details, but in fact, these motors are actually like motors, and there are traffic jams and other things. Well, so the last talk, I see that has brought a smile to some faces, right? The last topic is about crowds. Have you all ever been in a crowd? At the suburban stations? Where? Where? Mumbai, where? Couldn't hear. Local trains. Good example. Yeah. But Mumbai local train is not, I mean, it's it's gone off. Okay. In a Mumbai local train, I mean, basically once you're in, you can't move. So there's no movement, but we'll leave that out. Suppose we have a crowd. Okay, so how will people actually move? Let's see. So suppose you have to escape from a room that's full of smoke. There are two exits. One is very, empty, and the other is full. It turns out most people will go to the full one. Why? Because they think there must be something wrong with the other one. That's why people are not going there. So everybody tries to go in a crowd. So this is not logical, but that's how people behave. So anyway, you can make a model of people in a crowd. So this is again done by people from physics. And what they did is that they did a simulation. You know what simulation is? A computer modeling. And they put certain features to each person, and then they saw what happens. Now, I'll just tell you how people behave when they're in a crowd. The first thing is that if you're walking, and if there's a very tall person in front of you, the first thing people do is to somehow try to get around that. Or if you're driving and there's a very large lorry in front of you, tendency is to avoid that so that you get a clear view. So you have to model it in that way. There's also a tendency to follow the crowd. If there's a crowd, as here, people like to follow the crowd because they feel it's safe. Everybody is going there, let me also go. May not be logical, but they do that. So as a result, there are very strange things that happen, and this is well documented in the study of crowds, that if you widen a corridor, you would think that will help people. It actually slows down because people try to overtake and get stuck. If you place obstacles in the middle of the corridor, it actually helps flow because people go around and then they go in a systematic way. And if you have empty exits, nobody goes there. Is this of any use? Well, so here. So this approach of crowd dynamics has saved hundreds of lives. This is during the Hajj pilgrimage in Mecca. And there was a physicist named Dirk Helbing, I won't get into the details, who was asked to look into why are there stampedes every time. And he put in a model like the one we had here, analyzed the problem, and came up with a very simple solution of how to place entrances and exits. And after that, the situation improved dramatically. So I think authorities world over can benefit from some insights from these sorts of things. So I think my talk is pretty much over. So here's the conclusion. Anybody happy? Right. Not happy with the talk, but happy that it's over. Yes. So let me say in 4 lines what I've tried to tell you. First, a random walk. Remember that one thing you should see in any lecture that you go to, you can't know everything, no matter what. But try to remember 1 or 2 things and ask yourself after 1 week, do I remember 1 or 2 things? Anyway, so come back to this. So remember what a random walk is, okay? Yeah. I think it's very entertaining. It's very instructive. It's interesting. As I've told you, it has many, many applications, and it also underlies some models of traffic and crowds. Okay, so with that, let me stop. Let me give an acknowledgement of support that has enabled me to do what? To work on random walks all these years. So these are my support agencies, and I'll leave this on where for some time in case there are further questions. Okay, with that, let me stop.
Thank you, sir. What an enlightening session we have just had. And now that we have had the privilege of absorbing such profound knowledge, it's time to delve deeper. And we will now begin with our interactive session. Students, this is your chance to interact, engage directly with Sir, and delve into the aspects of the topic that sparked your curiosity. So we encourage you to ask questions, share your thoughts, and engage in a constructive discussion. If you have a question, please raise your hand and the mic will be brought to you.
Did you raise your hand? No. Yes.
So what is the cause for Brownian motion?
The cause for Brownian motion is that, let us recall what Brownian motion is. You have a very large particle which is in a liquid which is made of small molecules. What happens is that the molecules are moving all the time, and in any short time, the large object is hit by many, many, many molecules from all its sides. Do you understand what I'm saying? So here's a large particle. It's hit from here, there, all over the place. And since there are so many of these hits, they're practically random. So the effective hitting force or the impulse will be in one direction at one point and in some other direction at another point. So because of this collective bombardment by molecules, the large object does effectively a random move.
So if there is no collision between particles,
Yes.
will it only move in one direction?
Yes, indeed. However, yeah, so if there's no collision between particles, a single particle will follow Newton's laws and just move in one direction. However, if, as I said, if there are particles and there are hits, now in between one hit and another, the particle is moving in a straight line, and then it deflects off and so on. So you remember that video with the red balls that I showed you?
Yeah.
The balls are hitting each other, and then we focused on one ball, and we asked what did that, and then it traced out that white color trajectory, and that at least looks very much and is a random walk. But you're absolutely right. If there's nothing at all, then it just goes.
Yeah.
Right.
Sir, how would you derive the Avogadro's number from Brownian motion?
That's a very interesting question, and the answer is actually worked out in the Einstein paper, but let me try to give you a flavor of the argument. All right. So, you know, we've been talking about random walks, but the other context or the word that is often used in material science and physics to describe this is diffusion. Diffusion means, you know, essentially random walk motion. Now, how fast does something diffuse? That depends on the temperature. Einstein, you know, was able to give an argument of the relation between, you know, this diffusion constant and temperature. Now, but the relationship, interestingly, involves K. K being something that is known as the Boltzmann constant. Are you aware of the Boltzmann constant? Children, have you heard of Boltzmann constant? Probably not. Okay. The Boltzmann constant is given by, have you all heard, does anybody know the ideal gas equation of state? Tell nRT, right? So that R is very well measured and we know what R is. Now, the Boltzmann constant K is capital R, which was just mentioned, divided by Avogadro's number. Okay, so you have to put all these pieces together. Basically, Einstein said, measure the diffusion constant. Okay, if you know the diffusion constant, then from this chain of reasoning, you will be able to find the Boltzmann constant. If you know the Boltzmann constant, then you know the ratio of R over Avogadro number. R is well measured, so you can find Avogadro's number. This is the essence of the argument. Okay, but you know, Einstein wrote his papers very beautifully and simply. So if you get a chance, read them. I mean, you won't understand everything, but you'll understand quite a lot. 1905, Zeitschrift article by Einstein, written in German, but there are English translations today, easily available on the internet. Or read about it somewhere else. But this is the argument. Did I answer you? Questioner? Is the answer okay? Thank you. I got a nod. Yeah.
Sir, why is radioactivity the only truly random thing in nature?
Yeah, that's a profound question. I mean, I don't know. I mean, let's put it that way. Scientists don't know of. Okay, the first question is, suppose I take a coin and toss it, right? For many practical purposes, it is random. The answer is either heads or tails. But in principle, if I knew where the coin is and I knew with what impulse I, you know, toss it up, I knew everything about the, you know, viscosity of air and the locations of molecules, I can work out in principle using classical mechanics what the coin will do. So it's, in that sense, the coin tossing is not truly random. Now you examine all sorts of so-called random events and you'll find that actually they are not random, you know. But the only thing that seems to be, you know, really intrinsically random is radioactivity. If you ask me why is this the only one, I don't have an answer. I don't know. It is. It is. Maybe there's something else, but I don't know of it. Now ask before anybody else asks.
Good afternoon, sir.
No, huh? How the physical approach, how, but this is a very broad question. Physical approach to what? Or to anything? Or is asking, in general, is that what you're asking? Okay, yeah, I mean, I have to think a little bit. I mean, first of all, I have to think about what you mean by physical approach. You know, in physics, in all of science, you know, there's a hypothesis. You make a theory and you go along with it and you make a small prediction and then you see whether it works or not. And if it doesn't work, you throw the theory away. Come up with something better. And so that is what I would call a physical approach. Now, how does the physical approach help? Well, it helps in getting understanding, meaning that if I have some phenomenon that I keep looking at, and each time there's something different that happens, if I know what really matters, you know, what is the important thing that determines it, that is surely going to be very useful, because if I know that, I can control it, I can change it, I can do. So the aim is to find a small number of things, simple things, that I can adjust so as to get a better handle on it. So I can do something better with it. For instance, so let me give you the example of this crowd dynamics, okay? Physical approach to crowds seems a little daunting, but it works. So if you don't mind, I'll tell you a small story about Helbing. Helbing was the physicist who did this.
Small story.
So these authorities had given him videos of the stampede. Now, what he noticed, he watched many of these videos, and then he noticed one thing. He noticed that before the stampede, you know what stampede is, right? You know, uncontrolled movement. I was once in a crowd and in a near stampede. It's very frightening. Try not to get into that situation. Anyway, but before the stampede occurred, as you watched the video, quite a bit before that, maybe I don't remember, a few seconds before that, there was some strange movement in the crowd. Now, this movement, okay, was very weird. It had nothing to do with the stampede, but whenever that happened, a little while later, there was a stampede. Now, this movement, he had often seen in his computer simulations. So he knew exactly why it happens, and he also knew how to get rid of it. So his approach was get rid of that movement and the stampede will go, and it worked. So a physical approach was useful.
Sir,
Where are you? Yes.
Could you please explain the problem of random motion given by Carl Person again?
Yes.
I didn't get how he got the answer for it.
Oh, no. Okay, I'll tell you. This is quite interesting. Yeah, so as I said, Pearson was a statistician. His interest was actually in biology and heredity. You know, how are some traits passed on. Anyway, that is incidental. But what Carl Pearson did was to realize that here, this whole problem can be recast as a question on random walks, which he did. Okay, so in his first, the first paper that he sent out, he asks the question, can anybody tell me where, how to find this? What happened in the intervening 2 or 3 weeks is that many people wrote to him and they gave him the answer. And the mathematical working out of the answer was actually in a book or a paper by Lord Rayleigh. Rayleigh was a well-known physicist of that era. And he had worked out the mathematics of sound wave propagation, of all things. How sound propagates. So Pearson, if you read his answer, is very humble. He says, look, I should have known the answer, but my reading has become a little less than it was. And I had no idea that I will find the answer in a book on sound. So he found the mathematical working out in this book of sound, worked out earlier by Raleigh, and that's how he found the answer. But the thing that Pearson did, that Raleigh did not, why do we remember Pearson at all? It's because he coined this idea of a random walk. You know, Raleigh had worked it out, but in a very nice mathematical way, without giving it a little, what should I say, life. Pearson gave life to the problem by invoking this person who's doing this strange walk.
Sir?
Where are you? Yeah.
Sir, here. So can you please explain that how did we mathematically arrive at the conclusion that the distance covered is root x by, sorry, the displacement covered is root x by the body in a random motion?
Yeah. So there are many ways to approach the problem. The one I told you about, I personally found in, have you all heard of the Feynman lectures on physics? Okay, there's a very delightful series of books called Lectures on Physics by Richard Feynman. Feynman was one of the great physicists of the last century. And he has these three books, Volume 1, Volume 2, and Volume 3, where he looks at physics in a very original way. And this derivation that I showed you is from Volume 1 of Richard Feynman's book. Okay, now there are many other derivations which are much more complicated, so I won't get into that. But would you like me to go over this thing again? Or let me try to explain. I mean, you know, we won't go to the video. Okay, so try to follow the argument. Here I am at time t, at this position. I've arrived there somehow from some other starting place or Nami. Now I want to ask at the next step. So I'm asking for the location at the next step. Now it's clear that at time t plus 1 is related to the location of time t by just one step, this way or that way. But which way is random? We don't know whether it came from here or from there.
So I had a doubt at this point too.
Yes.
Why only +1 or -1? Like, could be in any direction, right?
Yeah, so for simplicity, I've taken, you know, just to be able to do the algebra easily. And otherwise, you need not make that assumption. If you have steps of any length, but likely on the left and the right. Okay, so in that, and that is not much harder to prove. So if you meet me after this, you can prove it in 2 minutes, but let me not attempt the proof right now. Yes.
I like to ask about the empty lattices random movement that you mentioned in the beginning of the speech.
Yes.
Sir, how do empty lattices in imperfect crystals make random walks?
Well, it's like this. It's an empty lattice, it's an empty point. The lattice is the whole thing, okay? You understand what I'm saying? Okay. So here is a point where there's nothing, but it's surrounded by 4 points, or whatever number of points, where there is an atom. Now, at any temperature, you know the effect of temperature normally is to give a push to things. They move around, vibrate. So if the atom next to it vibrates a lot, it jumps in to where the empty spot was. Okay. Now imagine that there are 4 places. You can't tell which one will actually jump in. Maybe this, maybe that, maybe this, maybe that. Right? Suppose this jumped. Okay, at that point, this empty site becomes full. but the place that this atom came from becomes empty, right? So it's as if the empty site moved one step at random. And
Sir, so it only appears that the empty space in the lattice is moving and not that the empty space is actually moving.
yes, you're right way. It only appears that way, but realize immediately that this is a much simpler description. The empty spot is moving. Okay, you can go back and transcribe to atoms jumping, but the fact that you can just say that this is moving and it's doing a random walk is enough. So when you analyze the strength of materials, you know, the occurrence of these are called vacancies is very, very important, and they determine the mechanical properties of the solid. Interestingly, the question of what happens if there are many vacancies together is also very important, and that can lead to failure and other things in the material. We won't get into that.
Sir,
Where are you?
sir, what are the applications of random walks in biology and economics? I saw it in the presentation.
In biology, first of all, Carl Pierce came from there is always an element of probability in how, see, today we know there are genes, there is DNA, etc., etc. We know much more. But as you realize, the process of transmission is random. So that's a fundamental way in which it enters. Second, and something on a different scale, how do ants move? Good way of yes, communicating with each other, and that is they drop this chemical which is called a pheromone, and the other ants which come along sense it and they move along roughly that way. But the first ant, a single ant which is looking for something, you know, it actually does a random walk. I mean, if you watch, I mean, you should watch ants once in a while, you know, and you see what it does, and you'll see that it's actually darting around and doing a random walk. So it's third example, and then I'll stop. So there was a question here that why did I choose only plus or minus one? Answer, I did it for simplicity. You know, so you could think of another type of walk, random walk, and I skipped those slides that we had them, where at each instant the walker decides how long the step will be. Maybe it will take and then suddenly long. So when you watch that motion, you find that it's erratic and then sudden large something. Now that actually is the flight of a mosquito, if you think about it. Because, you know, why are mosquitoes that so hard to catch? Because then suddenly then they move. So not only mosquitoes, but many animals move in this way. They do something local and then suddenly move out. So the study of random walks of this sort also helps to us.
Sir?
Where? Yes.
Good afternoon, sir.
Good afternoon.
My question is that can the study of random walk help in tracing and observing the celestial objects in space, since space is filled with uncertainties and there are many gravitational fields all bundled up together?
Yes. Okay. So this is a very interesting question. Have you heard the name of Subramaniam Chandrasekhar? Let me ask you. Has anybody heard of Chandrasekhar? Yes? In what context? Chandrasekhar limit, correct. See, Chandrasekhar was an astounding and amazing person. His interest was astrophysics, but in 1943, he wrote an article which was called Stochastic Processes in Physics and Astronomy. Stochastic is a big word, let me explain. Stochastic is something that you cannot predict. This way, that way, this way, that way. It's a beautiful article. Until today, when students come to work with me, I mean, on something or the other, first thing I tell them, read Chandrasekhar's article. Now, why did I cite Chandrasekhar? His article starts out with the random walk, and many of the things I talked about are, in the article. But remember, Chandrasekhar is an astrophysicist. So why was he even interested in random walks? The answer is, and if you read further into his paper, you'll find it. Let's look on scales not outside our galaxy, but within the galaxy. By the way, anybody know the name of our galaxy? Well done. Good. Milky Way. Right. So in the Milky Way, you have stars. Anybody know roughly how many? Huh? 1 trillion. What is trillion? 10 to the? Okay. Anyway, some large number. About 10 to the 10 or 11 is what I thought, but I could be wrong. Anyway, now these stars are not uniform, you know. First of all, there is, of course, the disk and all that. But often stars are in clusters and they interact with each other through gravity. It turns out Chandrasekhar analyzed this. He analyzed the data on what are called stellar clusters. And he found that the best way to model a stellar cluster is through a bunch of random walkers. And of course, it has to be adapted to the long range force of gravity which is there. But he adapted it. He was very powerful mathematically. And he, amazingly, it works. You know, that's one example. There are many, many, many other examples. I will not get into those. But and Chandrasekhar is such an inspiring character. There's so many stories about him. If you all have the time and interest, I'll tell you.
Sir,
Where? Yes.
Sir, my doubt is the path of the random walk is really random or is just a pattern, or we just need to observe it for a longer time. Like, is it really random?
Well, see, very rarely is something really random. But if it's effectively random, it's random. I mean, for our purposes. You know, it goes back to what do you want to do? You know, if you want to describe things, one need not always go to the atomic level to describe everything, right? So there are certain levels of description. So at a certain level of description, the movement of a colloidal particle in a liquid is basically random. This was Einstein's assumption, you know, when he analyzed this. If you go back and tell me, no, there are so many Avogadro number of molecules in there, and they are actually doing Newton law pushing, you would be more correct, but it would not be a useful point of view. So, answer, most of the situations in which we have random walks, things are not truly random in that sense. In principle, they are not, but in practice, they are so close to random that it's a better way to start. See, physics looks for simple explanations. Simple is good. You know, often when students enter research, they think that by writing large equations and, you know, doing this is a good thing to do. Answer is no. You should be able to write large equations, but try to find simple answers. Simple is good. And random walks are simple.
Thank you, sir.
Thank you, all the children, for such genuinely involved questions. Your doubts are so keenly addressed by Sir. We'll take one last question before we end the interactive session. The last question.
Sir, why is it that we are...
Oh, okay, two last questions. One, and he's been waiting for a long time. Can we have two last questions?
Yes, sir. We'll have two last questions.
Okay.
So why is it that we are studying about the random walks? Because we as a human have a tendency to study about only the things which have utility to us, which benefits us. So why are we studying about random walks? Why are we researching so deep?
Well, the answer is that I mean, it goes back to the previous question. Many things that happen, even if there are other intentions, turn out to be random. Okay? And therefore, it pays to study what would happen if you had purely random behavior. So it's like this. In physics, when is a model or when is a way of thinking important? It is important not if it answers an exact question that you may have or I may have, but if it provides a way of thinking. The way of thinking is very important, and the random walk is a simple enough idea that the way of thinking along those lines we can understand. The moment we have understanding, that's a great thing. When you come back to the question of benefit and so on, yes, those are important and cannot be left out. Like when you deal with crowds, you cannot leave out the aspect of human behavior, but the random walk is a start. It's a start. There was this question here, and maybe one more. Okay, can we take two more? Sorry. I could not hear. What is polymer conformation? Yeah, I'm sorry I did not discuss this at all, but it's actually a completely different application of random walks. So think about a polymer. Have you all heard about polymers? Yes? Polymer. A polymer molecule is a long molecule. Okay. It's made of small objects called monomers. Okay, so let me try to describe a monomer. I mean, okay, so here's one monomer, here's another. So there's a chemical bond which attaches the two, and at the end of this is another, and another, and another. And this repeats roughly 10 or 20,000 times. Now, remember what you know about chemical bonding. There's an angle which is preferred. But if that angle is anything, it means that the next monomer can lie anywhere in a cone, right? Because it keeps the same angle. And then the next, and so on. So you have these monomers, and each one is doing a little bit of a movement on a cone, each monomer. When you have many of these, the whole object looks exactly like a random walk in 3 dimensions. So that's the answer. I mean, the actual geometry of a polymer is very well represented by the trajectory of a random walk in 3 dimensions. Was that your question? Yes. And okay, I mean, yeah, there's a lot of neutron scattering data which supports this. We will not get into that. Yes. There was one last question now. Yes. Yes. Take this and ask.
So if we
No. Everybody wants to hear.
So if we move in a circular motion, is that a random walk?
If you're moving, I mean, like this in a circle, and you keep doing that, that is not a random walk. But there are very interesting questions about circular motion, which is random. So you move along a circle for a while, and then you move backward and then forward. Often, you know, where does this happen? As you know, any wave, like light or something, has an amplitude and a phase. The phase you can imagine as something on a circle. Now, often there are random events which change the phase randomly. So if you have random circular motion, that's like dephasing. Okay. So
Thank you so much. Can we hear it again? Thunderous applause for our esteemed speaker. so enthusiastically addressing and interacting with our young minds. Students, I hope you found today's session both informative and motivating. Remember, the knowledge and ideas shared here are tools that you carry forward in your academic journey and beyond. Now, at this point, we'd like to open the floor to any other esteemed dignitary present here who may wish to contribute their thoughts or address the audience.
Can I take a photo of you all? Okay. Okay, I got something. Oh my God. Okay. This is me. Did you do it? Who drew it?
Creative genius of
Thank
our
you.
young children in the form of a beautiful picture. And on the spot,
Look at this artist.
sketch by a young artist.
What's your name? Nilantra. Thank you very much. Is this for me? Thank you. I will treasure it. Thank you very much. Okay. I mean, I'm all for it, but the organizers have to allow it. There's a doubt. Yeah, it happens all the time.
I'd like to invite Dr. S. Sugilal for addressing the audience.
Meet me a little while later. Yeah. Ah, yeah. Where's the mic? Yeah.
Survives third dimension only possible in space.
I can't hear.
Survives third dimension only possible in space.
No, it's not possible only in space. It's certainly by space you mean outer space? No, it's certainly possible anywhere. I mean, I haven't understood the question.
It's like the third dimension motion in Z axis. Sir, in why is third dimension motion possible only in the outer space?
Okay, if I understand it, the question is why is the third dimension possible only in outer space? The answer is it's not possible only in outer space, it's here also. It's just that, you know, why could I not do a random walk in 3 dimensions? Because of gravity. I mean, I could not start jumping around, you know. So if I had been, so do you understand what I'm saying? It's easy for me to do a random walk in 2 dimensions. It's not easy for me to do a third dimension because I am pulled down by gravity. But if you have a light object, like a dust particle, you should watch when there's a beam of sunlight and these dust particles, you'll see them moving, and they're moving in 3 dimensions. And each one is doing a random walk. Look around you and you'll see random walks everywhere. 1 dimension, 2 dimensions, 3 dimensions. Okay?
Dear children,
Sir, you told that a molecule basically takes infinite time from the starting point to the starting point. So how is it possible that it takes infinite time?
Yeah, no. So you're right. It's a little confusing. His question is, you know, how can it be that somebody takes infinitely long to come back? No, so the answer is,
Other students, please listen carefully.
the answer is that what I talked about is the average time to come back, and I said that is infinity. And infinity means the following, that if I take a very long time, so you saw those funny graphs with the leads changing over 10,000 steps and so on. If I had run the game, not for 10,000 steps, but let's say 10 million steps, then the longest lead would have been much longer. So there's always a probability to have a yet longer lead. The probability of doing that can be found mathematically. When you take an average value of that, you find that that is infinite. Okay? So, yes, if you have 10,000 things, it can't be infinite, but the longer you make it, it is. Yeah.
You told that the random walk can be applied in various types of science. So can you tell like how we know that this could be applied in this science and like where it is applied currently?
Yeah. How to know? Well, no, so first of all, the best approach is you understand what random walk is. Okay. Once you've understood it, you will find often very strangely and without any expectation of it being there is an underlying random walk. I mean, it's one of these things. If a model, if an idea is basic enough, then without your wanting it to happen, it happens. I mean, wherever you look, you'll find it. So you can't go around looking for examples which have this. The examples will come to you.
Thank you, students. We do appreciate your curiosity and keenness. If you still have more questions, you can write it and submit it to us for it to be addressed later. And once again, a round of applause. We request sir to please be seated.
Thank you.
And now I once again invite Dr. G. Sugilal, who would like to address you on this occasion.
Dear students, I just came over here.
Oh, okay. Thank you.
Just to thank Professor Barma, who taught you how to become philosophers. I don't know whether you have realized it or not. He has picked up a topic which is very, very difficult to comprehend. But through his nice illustration, he has taught you how to invoke your imagination and how to think like a philosopher and how to derive conclusions, how to approach a problem mathematically, scientifically, and philosophically. We could not conceive this topic because we are perhaps grown too much that we don't make random walks very often. We are following targeted walks. So that may be the reason why you could not probably in the beginning realize this topic, the random walk. But for the nature, this is really a reality. And he has illustrated several aspects in the nature which is following random walks. And then he explained to you how to visualize various possibilities and then come to some mathematical theories to quantify these random walks. So dear students, essentially he did how to think, which probably, when we are following your routine syllabus, when you are preparing your examinations, you may not be encountering this kind of thought processes. So by this program, the AES really wanted to tell you how you people can start imagining, which is beyond your normal classes. So he has really taught you, and I would like to take this opportunity to thank Professor Barma in invoking your real potential, how to become philosophers. And I thank Professor Barma once again, and it was very amazing to see the interactions between Professor Barma and the students.
Thank you.
And many of your questions went beyond my imagination. Though it was a very difficult topic, but you have actively participated and communicated with the speaker. So I thank the children for the same. And we look forward to such fruitful programs in future. Thank you, AES. Thank you, sir.
Thank you very much. And I must say I really appreciated the patience of the audience, young though they are, and also the nature of the questions, which to me revealed really very deep thought processes in very young people. Thank you.
Thank you, sir. As we inch to the close of this event, let's dive in a special moment to honor and express our gratitude to our esteemed speaker. With these words, I humbly invite all the dignitaries on stage for memento presentation. I request Inu ma'am to escort Chairman AES, Shri Ranajit Kumar, Secretary AES, Shri S.K. Lahiri, Chairman LMC, Shri Dr. G. Sugilal, Principal and Head Academic Unit, Dr. Mrs. Neena Bopaya, and Principal ACS 3, Shri Sanjeev Ghosh, to join on stage. I would also like to welcome Coordinating Principal ACS 1, Shri Kamlesh Kumar, to join the dignitaries. And additionally, we would like to have Shri Arnab K, art teacher of ACS 3, to join all the dignitaries on the stage. Now, may I request our Honorable Chairman, Shri Ranajit Kumar, to present the memento to our esteemed speaker. This is a beautiful portrait which has been deftly made by ACS 3 art teacher, Shri Arnab K. A huge round of applause. We hope this memento serves as a lasting reminder of our appreciation for your valuable presence. This is a small gesture which symbolizes our gratitude for your time, expertise, and wisdom that you have shared with the students today. Thank you, one and all.
Thank you, everybody.
So the picture is now complete as all the principals have joined in for a beautiful capturing of this moment. Thank you once again. Feeling gratitude and not expressing it is like wrapping a present and not giving it. So, to give that present, I would humbly request our sagacious and resourceful Principal ACS 5, Ms. Inu Bansal, to propose the vote of thanks.
Good afternoon, everyone. It is my privilege to propose the vote of thanks on this occasion. First and foremost, I would like to express my heartfelt gratitude to our distinguished speaker, Professor Mustansir Barma. Sir, we a big thank you for sparing some time from your busy schedule and for having a one-to-one interactive session with our students. I think that is one of the memories all the students will cherish for their lifetime. So thank you very much, sir. My sincere thanks to Chairman ACS, Shri Ranjit Kumar sir, for entrusting us with this responsibility and guiding us whenever and wherever we stumbled. Thank you, sir. A big thanks to Secretary AS, Shri S.K. Lahiri, for his valuable suggestions and unwavering support. Heartfelt gratitude to Dr. G. Sugilal for his encouragement throughout the planning and execution of this event. Words alone cannot express my gratitude to Dr. Neena Bobaiya, Principal and Head Academic Unit. Madam, your unconditional support is our backbone and is deeply. We would like to please record our gratitude to all the heads of the Mumbai schools, with special mention to Dr. Kamlesh Kumar, Coordinating Principal and Principal ACS1 Mumbai, for guiding us at every step. Shri Santosh Jadhav, Principal ACS4 Mumbai, who is always just a phone call away and ready to assist us in any possible way. Shri Sanjeev sir, for providing very constructive inputs and helping us incorporate them to make this program successful, and also for arranging a very beautiful memento. Thank you, sir. Mr. Vijay Shukla sir, Principal ACS2 Mumbai, and his team for making arrangements for the live streaming of this event, ensuring all 30 schools of AECS across all over India could listen to Professor Barma's lecture and be enriched by it. So thanks a lot, sir. I extend my heartfelt gratitude to Shri Taran Kush, Vice Principal and Deputy Head Academic Unit. Sir is omnipresent as an invisible support system. So thank you, Tarun sir. Now coming to my own home turf, thanks to all the staff of ACS 5 Mumbai, including VP sir, HMM. It is you. It is because of you all who give me the strength and the courage to commit to conduct such kind of a program and ensure that whenever I'm committing anything, I will be able to deliver it and it will be a successful. So thank you to ACS 5 team. Thanks a lot. Now, sincere gratitude to the technical team and the cosmetic staff of DA Convention Center for making all necessary arrangements. Thanks to all the escort teachers of different schools for taking care of our children. Thank you. And lastly, thank you, dear students. You were the perfect audience today. Your enthusiasm and participation made this event truly special. So big thank you to all the students. Once again, thank you all for being here and contributing to the success of this event. Have a wonderful day. Thank you all.
Thank you, ma'am. I now request everyone to rise for the national anthem. Stand here,
नायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात गंगा विंध्य हिमाचल यमुना उच्छल जलधितरंगा तव शुभ नामे जागे तव शुभ आशीष मागे गाहे तव जय गाथा जय हे भारत भाग्य विधाता जय जय जय
भारत माता की, भारत माता की। Thank you, everyone. I request the students to please be seated. I request all the students to please be seated.